In this video, I am going to discuss about Unit 1 content of Computer Organization and Architecture. The first topic is Introduction to Number System. Whatever the data we are using inside the computer, that can be stored in the format of numbers only. There are different types of number systems are available. Here we should know how to convert from one number system into another number system. Before going to this topic, we should aware of how other number systems are represented. Here I illustrate how the normal decimal number from 0 to 16, and this is the equivalent 4-bit binary number. In octal number it contains only 0 to 7. After the 7 the next number is 10. In the same way after 17 the next number is 20. In hexadecimal, after the 9, there are 6 characters are there from A to F represented as 10, 11, 12, 13, 14 and 15. After this, the next number is 10. Now let's we talk about how to convert decimal number system into other number system. And this is the formula. Base means every number system having the base number. For decimal, 10 is the base. For binary number, 2 is the base number, and octal and hexadecimal 8 and 16 are base numbers. Base is otherwise called radix. So if you are converting given decimal number to any one of these number system, you should use this formula. If you want to convert this number system into decimal number system, you can use this formula. Let's see some example problem. First we learn how to convert decimal number into other number systems. Suppose the decimal number is 145. So the base of the binary number is 2. You should divide 145 by 2. You can get the quotient 72 and remainder 1. You repeat this step until you reach 1 or 0. Finally, you can write the result in this format. You can get the value like this. In next problem, 136 is the decimal number. We want to convert it into octal number. Using this same method, divide the given number by the base value, write the quotient here and write the remainder here. Same way, repeat this process. Finally, you can write the remainders in this order. So 210 is the equivalent octal number for the given decimal number 136. Let's check the second example also. In the third problem, so divide this 843 by 16, write the quotient here and write the remainder here. And again repeat this process, you can get 3 as the quotient and 4 is the remainder. Write the result in this manner. So 3 is the first digit, 4 is the second digit and 11 is the third digit. The decimal number 11 can be represented as B in hexadecimal. So it can be write like this. So up to this we learned how the decimal number can be converted into binary, octal and hexadecimal. Now we will see how these numbers can be converted into decimal using this formula. Now I want to convert one binary number into decimal number. So this is the given binary number. Write the binary number like this and multiply with the corresponding base and superscript values. After multiplying these values, you can add this value. Finally, you can get the corresponding decimal value. Let's we move to the octal to decimal. So this is the given octal number. Write this octal number and write the appropriate base and superscript values. So 64 plus 16 plus 5, the value is 85. The next problem is the given hexadecimal number is there. So write this value and write the appropriate base value with power values. Now you can get this result. So you should know how the numbers can be converted from decimal to other number system and other number system into decimal. Next, you should know how the conversion can be made between these number systems. Let's see how the binary number can be converted into octal number. So there is no direct method is there. So first we convert the binary into decimal, then decimal into octal. This is for when the question can be asked in part B or part C question. One shortcut method is that you can use this for 2 more questions or MCQs. Suppose the number is given like this. You can group them this number as 3 and get the corresponding value. The given number is fractional number. So this part is integer part and this part is fractional part. For this integer part, the grouping can be done from right to left. For fractional part, grouping can be done from left to right. First take the integer part. So these 3 numbers are the first group. Then 100 is the second group. Then 01 is the third group. Here one more bit is missing. You can add 0 so the value cannot be changed. For this fractional part, you should group from left to right. So first take 100 is the first group, then 0111 is the second group. Suppose if one more bit is there, you can add necessary zeros so the value cannot be changed. Now you just convert these equivalent binary number into octal number. 011 is nothing but 3, 100 is nothing but 4, 111 is nothing but 7. So in this way you can write the equivalent octal number from this binary number. So this is the final result, you can write like this. In the same way, you have to convert binary to hexadecimal. There is no direct method is there. So first you convert this binary number into decimal number, then decimal number into hexadecimal number. Like octal conversion, it's also having some shortcut method. So group them as a 4-bit numbers from right to left for the integer numbers. For fractional numbers, group 4 numbers from left to right. In this example, there is no fractional number. So you can group them as 4 from right to left. Then refer the table, you can convert this binary number into equivalent hexadecimal number. So all the number conversions are over. And one more thing you should learn, how this conversion can be happened in fractional number. Suppose binary number is given, it is fractional. You need to convert it into decimal number. We already know how to convert the binary number into decimal using this format. But now there is a extra numbers there in a fractional part. So you can add in this way. Remember this, the power value can be incremented in this way. But in fractional part, it can be denoted like this. Now you calculate this value. 2 power of minus 2 is nothing but 1 by 4, that is equivalent to 0.25. 2 power of minus 1 is nothing but 1 by 2, that is 0.50. We know already how to calculate this value. Add this value separately and then write like this. So instead of binary number, octal or hexadecimal number also given as fractional value. In that case, you can give the corresponding base value and calculate the same method and get the answer. Let's we move to the decimal to binary fractional number. Suppose the given number is 4.25. First we split the full number as well as fractional number. So this is the integer part and this is the fractional part. Integer part we already know how to calculate this. After calculation you can get 100. Then you can calculate the fractional part. So take this fractional part alone and multiply with the base value. Here we are going to convert the binary number. So I am multiplying this fractional value with 2. So the result is 0.50. Take this 0 as the one of the result and bring this 50 only in the next part. Then multiply with 2. Now we can get 100. Take this 1 into is the one of the result. Then bring this 00 into the next part. After that anything will be 0. So you can stop this calculation up to this part. So the results are 0 and 1. You can write in this order. So 0, 1 is the equivalent fractional part of this given number. So finally you can write the answer like this. So number systems are over. Let's move to the next topic is called coding system. Binary codes are just a way of representing information using zeros and ones. Anything in a computer that is numbers, letters or words, these are stored and processed as group of these binary bits. The binary codes are categorized into different ways. One is weighted binary code, non-weighted binary code, alphanumeric code and error detection code. These are all the corresponding examples. Weighted binary code is nothing but each and every bit having some weightage. For example, 843 is the decimal number. This position having the weightage 1, this position having the weightage 10 and this position having 100. In the same way, 101 is the binary number having this weightage. It helps to find the equivalent value. This 1 can be multiplied with 3. You can get 3. This 10 can be multiplied with 4, you can get 40. This 100 can be multiplied with 8, you can get 800. So 800 plus 40 plus 3, you can get this 843. In the same way, you can get the binary equivalent value. This weightage can be coming from this way. So 10 is the base value for this decimal number and the first precision having the value 0, 1 and 2 like this. In the same way, you can get this value. So this is called weighted binary code. In weighted binary code, the example is binary coded decimal. Binary coded decimal is one way of representing the binary numbers, in which each and every individual digit can be represented as the binary number in the 4-bit format. So 2 can be written like this. The actual binary value is 10 only, but we should write in the 4-bit format. In the same way, 4 can be written like this. Let's compare the decimal number and equivalent BCD. This BCD number almost similar to the 4-bit binary number up to 0 to 9. Then after that 10 can be written in this way in binary number. But in BCD number 10 is the 2-digit number. So 1 can be written as the 4-bit format. 0 can be written as the 4-bit format. So this is the main difference between normal binary number and BCD number. The advantage of BCD number is representation is very simple. Suppose the decimal number is 85 means you can write the value 8 and 5 separately, but it occupies more number of spaces. The next binary code is non-weighted binary code. Why it is called non-weighted means the particular digit does not contain any weightage value. The examples are XS3 code and gray code. First see what is XS3 code. You just add the value 3 to the given binary number, that is called XS3 code. Suppose the given binary number is 10, you just add the value 3 to this and you can get the new value. The equivalent decimal value is 2. If you are adding 2 plus 3, you can get 5. So write the equivalent binary value for the 5. So this is called the XS3 code for this given binary number. Let's see how this XS3 code can be populated. So this is the decimal number and equivalent binary number. Suppose this is the binary number mean this is the equivalent XS3 code. So each code having plus 3 value. Suppose if you want to convert this binary number into XS3 code means you just add the value 3 and you can get the new code. In the same way, if you want to convert XS3 code into binary means you just subtract the value 3 and you can get the equivalent binary code. Then the next non-weighted binary code is called gray. Gray code is a special code. It is used for in different places. The special quality of gray code is two successive values only differ by 1 bit. This is the equivalent gray code from these binary numbers. Take these two successive numbers. These two numbers only differ by only 1 bit. So 0 0 same bit, 0 0 same bit, 0 and 1. So these two numbers only differ from this only 1 bit. In the same way, you can compare second and third number. 0 0 is the same number, 1 1 is the same number, 0 and 1. So these two successive numbers can be only differ by this bit. But in case of binary number, this property is not available. So applying this quality that can be helpful for identifying the K-maps and error correction and detection and different communication mechanisms. So this gray code is otherwise called reflected binary code or unit distance code. Now you should know how to convert the given binary number into corresponding gray code. In this conversion process, the XOR gate is involved. This is the truth table for XOR gate. First we see how to convert binary number into gray code. Suppose this is the given binary number means first you write the first value here. Then compare these two values with this truth table. So 1 0. So 1 0 means the result is 1. You can write the result here. Then compare another two numbers 0 0. 0 0 means 0. You can write the result here. Then compare the next number 0 1. 0 1 means 1. So in this way you can write all the numbers. So this is the equivalent gray code. Next, how to convert this gray code into binary number. So write the first number directly here. Then compare the result with the second number. So 1 1 means the value is 0. You can write the 0 here. Then result is compared with the next number. 0 0 means the result is 0. So you can write the 0 here. So continue this process up to the last number. So this is the equivalent binary code for this given gray code. This is 3-bit gray code. Let me see what are the different size of gray code. And the next binary code is alphanumeric code. The best example is Haskell code. Haskell is the alphanumeric code used in digital computers to represent and exchange the data. Haskell is a 7-bit code, which means it can represent up to 128 different characters, including letters, numbers, punctuation marks, and control symbols. These ASCII characters are what make text readable for us as plain text and at the same time understandable for computers as data. The important ASCII codes are listed here. You just remember the starting point of these ASCII codes. Suppose if you want to know the ASCII code for 6 means, you can generate from this value. Suppose if you want to know the ASCII code for G means, if you know the starting point of the small case letter A as 97, you can easily generate this value. The last binary code is called error detection code. Example is parity codes. When data is transmitted over a network, the bits may sometimes get corrupted because of interference or some other network issues. These corrupted bits are what we call errors. To handle this, we use error detection techniques, which helps us to check whether an error has occurred in the data or not. Anyway, error detection only tells us that an error exists. It does not show how many bits were affected or what type of error it is. So to detect errors during transmission, the sender adds some extra bit along with the original data. These extra bits are called parity bits. At the receiving end, the receiver uses these additional bits to perform checks and verify the correctness of the data. If the data is found to be error-free, the receiver simply removes the extra bit, that is parity bit, and passes only the actual data. Let's see one real-time example for error detection in case of train. Before train start its journey, the final carriage should be marked as X. After reaching it, if any garage can be accidentally detached from this train, at the receiving end it can be easily identified by this mark. If the mark is present, that is the last garage, otherwise some train garages are missing. In the same way, the parity bits can be identify the error can be happened or not. There are two types of parity bits. One is even parity, another one is odd parity. Even parity is nothing but the number of bits including the parity bit is even. In odd parity, the number of bits should be odd including the parity bit. Let's see some example. In this example, even parity is used. This is actual data. Parity bit is added at the end. It may be 0 or 1 depending upon the number of 1 present in the actual data. Here the number of 1 present in the actual data is 3, that is odd number. So we have to make this entire data as the even number of ones, that is called even parity. So if we add the value 1, this entire thing having the even number of ones. So this data can be sent to the receiver. Suppose this data is corrupted means the total number of ones becomes odd number. So the receiver can easily identify some data is corrupted. So you can add either 0 or 1 depending upon the value given in the actual data. So this table illustrates how the extra bit can be added by odd parity as well as even parity. Suppose this is the given number. Here the total number of 1 is even. So for odd parity, you can add 1 as the extra bit to make them this data as the odd number count. Suppose if you are using even parity, this number is already having even number count. So it adds 0 here. So for this error detection method, you can use either odd parity or even parity. This is the working principle of parity check. Suppose if you are using even parity here, suppose this is the given data, the parity bit can be added here. The parity bit may be 0 or 1. Before going to decide this, you can count the number of 1 here. So there are 5 ones are there, that is odd count is there. So you can add 1. So this entire data becomes even number count. So this is called even parity. So this data can be sent to the receiver. Now the receiver check whether the count is even number or not. If it is even number, the receiver understand the data is not corrupted. Otherwise, it treats as a corrupted data. The advantage of this method is simple, but the disadvantage is sometimes it may not identify the error. Suppose the two data becomes corrupted means the receiver side does not identify this error. So the binary codes are over. Let's move to the next topic called binary arithmetic. For this binary arithmetic, Already some detailed videos are posted in this channel. I provide the links given in the description. So in this part, so many problems can be asked. So you should know how to add and subtract multiplication division by two binary numbers, whether it is full number or fractional numbers. In the same way, BCD arithmetic also there. So refer this video and practice more problems. The last topic is logic gates, and basics of logic gates already given in separate video. Check the link. In this topic, problems can be asked in the part of realization of logic gates. Realization of logic gates is nothing but one logic gate can be generated from other logic gate. Usually, these two logic gates can be used to generate another logic gates. That's why it's called universal logic gates. Let's we see how the NAND gate can be used to generate other logic gates. First take the NOT gate. This is the NAND gate symbol and truth table, and this is the NOT gate symbol and truth table. We have to get this output using this NAND gate. When comparing these two gates, this is two input gate and this is single input gate. So first I check the truth table. What are the rows or both the inputs are same. And here, if the value is 0, the output is 1. If the value is 1, the output is 0. So I can remove the one input. So the first input can be taken as the second input. So if the value of A is 0 means you can get the value 1. Suppose the value of A is 1 means you can get 0 here. So if you are connecting the NAND gate like this, you can get the NOT gate output. This is called realization. So in the same way you can develop some other gates also. Now let's see how the AND gate can be generated from NAND gate. We already know NAND gate is nothing but the combination of AND gate and NOT gate. If the input is A and B, the output in this point A dot B, and in this point A dot B whole bar. So this is the actual NAND gate output. If you are connecting one more NOT gate at the end, you can get the inverted output like this. So these two bars can be cancelled. You can get A dot B. So you can connect NOT gate here. We already know NOT gate can be designed by NAND gate like this. So you can get the AND gate output for these two NAND gates connected in this way. Next we will see how OR gate can be generated from NAND gate. This is the OR gate symbol and corresponding truth table. We know the expression of the output of NAND gate is A dot B whole bar. In De Morgan's law, A dot B whole bar can be written like this. What we expected A plus B, but the result having the A bar and B bar. So instead of giving A, first you give the A bar input, then you give the B bar input. If these two values sent into the NAND gate, you can get the result like this. So this can be written as per the De Morgan's law. You just treat A dash is the X, B dash is the Y. Then you can get this value. Then these two bars can be cancelled. You can get A plus B. So A plus B is the expected value. So using this idea, you can generate the OR gate using NAND gate. So A bar can be generated in this way. B bar can be generated in this way. Both are again sent into the NAND gate. You can get A plus B. Next, NAND gate can be used to generate NOR gate. We already know NOR gate is nothing but OR and NOT gate combination can be connected like this. So if you are adding another NOT gate, you can get this output. So we already developed OR gate by using NAND gate. Just convert the output into inverted output using this mechanism. You can get NOR gate output. The next one is NAND gate to XOR gate. This is the XOR gate truth table as well as the expression. There are two ways to generate XOR gate from NAND gate. First one is you should draw this expression as a diagram. So A can be converted into A bar and B input can be taken. Both are subjected into AND gate. So this part is over. For this part A can be taken here. So B can be converted into B bar and subjected into another AND gate. So you can get this result. After these two results received, you can do the OR gate here and get the result. So from this diagram, you can convert the corresponding logic gate into NAND gate. But it takes more number of logic gates. For example, OR gate can be achieved by 3 NAND gates. AND gates can be achieved by 2 NAND gates. So 2 plus 2, 4, 4 plus 3 7, 8 and 9. So to achieve this operation, we should have 9 NAND gates. For the simplification, we can go to the second method. So before Boolean simplification, we have to conclude this. NOT gate can be achieved by this formula. We already realized this circuit. AND gate can be achieved by this formula and OR gate can be achieved by this formula. Now I am going to take one expression. The first intermediate value is n1, that is nothing but I want to get a dot b whole bar. Then the first input and this intermediate input can be subjected into NAND gate. So a dot b whole bar and whole bar. If you multiply these two numbers, you can get a dot b bar and whole bar. In the same way, second intermediate result, that is n3, can be found the second input with this n1 value. Then you can get a bar dot b whole bar. Now these two values can be subjected into NAND gate. I can get this value. After the simplification, I can get a dot b bar dot a bar dot b. So using this derivation, you can get the circuit like this. So here only 4 NAND gates can be used. So this can be get from the Boolean algebra simplification. In your examination, you can do any one, but this is the professional way of design. And the last one is XNOR gate can be designed from NAND gate. First you compare XOR gate and XNOR gate. So XNOR gate get the inverted output from XOR gate. So we already designed XOR gate from NAND gate. You just add the NOT gate operation here, then you can get the XNOR gate. So this is the one way. And another way is some simplification of Boolean algebra. So this is the formula. After applying the De Morgan's law, you can get this value. So design this circuit as per this formula, you can get the XNOR gate. You can prove this output using truth table also. In your examination, don't write the destination gate directly. You should tell how this gate can be combined and generate by means of truth table also. So NAND gate to other gates can be over. So in the same way, NOR gate can be used to generate other gates. The same techniques can be used here. So I just go through how other gates can be generated from NOR gate. So this is NOT gate from NOR gate. This is AND gate from NOR gate. You just compare NAND to OR in previous section. The same mechanism can be used here. So try to understand the shortcut method. And this is OR gate from NOR gate. And this is NAND gate from NOR gate. Just compare this structure from previous one. In this arrangement using NAND gate, you can get the NOR gate output. In the same structure used here, using NOR gate, you can get the NAND gate. So you can easily remember this realization using this shortcut method. And this is NOR gate to XOR gate. And this one is NOR gate to XNOR gate. Now all the topics are over. I hope you understand well about this unit. Don't forget to download the notes available in description. Thank you for watching and learning with me. See you in next session.